Well, hi everybody. I'm Dan Clare from Diamond. I'm here to do the lecture number 5, which is on the contrast transfer function and CTF correction. So I'm going to go through a number of different things this morning, which are listed on this front slide. So we'll start off with the types of contrast, a bit about the weak phase approximation, then go into the contrast transfer function, then some chat about determining the focus, and then CTF correction methods. I've put in a little bit about CTF aliasing. This is important for higher resolution work. Then something about CTF related to tilted images, a little bit about phase plates, and then just a plug for EBIC, which is based at Diamond and is where I currently work. So yeah, I suppose the usual thing is to thank the organisers for letting me give this talk, so I better do that. Okay, so let's start off with the first slide. So this is just looking at contrast transfer. So this is again one of Helen's favourite pictures. So we've got our cow down here. So if we look at the contrast transfer as a kind of a 2D plot where we have relative contrast on the x-axis, sorry, on the y-axis, and spatial frequency on the x-axis. So again, at the bottom, you can see this spatial frequency. You go from low spatial frequencies to high spatial frequency, which corresponds to low resolution coarse details at this end to high resolution fine details at this end. So if we had perfect optics, so this red line here, you'd see you'd get the perfect image recorded of your object of interest. If you, in the case now with direct electron detectors, we're probably more in this kind of real optics region where we get a pretty good representation of our object, but there are still some blurring effects from the optics. And then the good old days of a few years back when we didn't have direct electron detectors, we were probably more in this bad optics area where you just get pretty horrible images of your object. Then obviously there's also, you can get, this is positive contrast, but you can also get negative contrast, in which your contrast is inverted in your object of interest. So the types of contrast in TEM are generated by two different methods. So we have amplitude objects. So this is essentially where you have your electron wave, it interacts with your object of interest, and you get a reduction in the amplitude of your wave, which is shown here as this height, the peak height is reduced post object. So, and this can be measured by your detector as a change in intensity. The other thing I should note about this depiction is, you know, your wave has not only this amplitude value, but it also has a phase. So how many times it oscillates within 360 degrees. You also have a wavelength which defines the how much it changes, or the length it takes to go from positive peak to positive peak. Okay, the main part of the talk and most of what we'll be talking about today, so amplitude objects is probably closer to negative stain, where you have heavy atoms, strong scattering objects. Most of what we're going to talk about today are phase objects. So they don't scatter electrons very strongly, and you don't get this amplitude reduction post object. So essentially you've got two waves going through your specimen here, and you get a small phase shift induced by your object. So you can see this is a difference in where these oscillations appear. So you can see here you've got the maximum transfer of your scattered wave and the minimum transfer of your unscattered wave. So these kind of wave diagrams can be represented in a different way with these kind of argon diagrams, which is I'm going to use quite a bit through the talk. And so you can represent your wave's amplitude as the length of the vector on here, and the phase of the wave as where it appears around this kind of 360-degree graph. And so you can see here we've got the unscattered versus the scattered. So the amplitudes are the same, it's just the relative phases are different. So in phase contrast TEM, so we have our sample, and we have in green here the incident electrons. So this is your electron wave that just goes through the sample, and the majority of the time it doesn't actually interact with your sample at all. And so that's your unscattered electron wave. It's in green here. So with phase contrast TEM, you get some of the electron wave is scattered by your sample, and the angle at which it's scattered is related to the resolution of the feature that it's scattering from. So at low angles, so you get this scattering effect. And the other thing I should mention is that when the electrons scatter from your sample, you get a 90-degree phase shift. So you can see that the unscattered and scattered part of the wave are 90 degrees apart. And you can see that here, again, represented on the argon diagram. So you've got essentially the amplitude as the vector length, and then the relative phase between the unscattered and scattered due to this initial 90-degree phase change of the scattered wave upon interaction with the sample. What happens is, as you increase the scattering angle, that increases the path length that the scattered electron wave covers. So when this is, the objective lens refocuses this back refocuses the electron back to form the image at the image plane here, you can see that this higher angle, the wave scattered at higher angles has traversed a larger distance, so that path length difference has added an additional phase shift, and now you can see that the relative phase of this scattered electron or scattered part of the wave is 180 versus 90 degrees. And that's pretty much what it says there. So one thing that we need to talk about is the weak phase approximation. So this for biological cryo-EM, this is where we work in. So essentially our EM image is a projection of the scattering density of our object modified by the contrast transfer function of the objective lens. So we make some assumptions that the object that we're looking at is made of light atoms, which in general they are. So they're weakly scattering. So that means we can take the phase shift or apply the weak phase object because of the small phase shift induced. So we can approximate the wave expression such that we only have to consider the first two terms. So essentially your exit wave is formed from your unscattered plus your scattered, your phase shifted or scattered part, and that's it. So you don't have to consider anything more. There are some additional things that affect this. So like some aberration, lens aberration, so spherical aberration of the objective lens, and most importantly, the defocus. So using this approximation, we can write a formula for how the contrast transfer function affects the spatial frequencies of our image. So So what you can see here is that there are a number of terms. So the main one that we're interested in is the defocus value. So that's how much defocus is going to be applied to the sample. And so essentially that is, as part of this, the only thing that we need to determine accurately is the defocus that we've applied. And then, because the rest of the terms we know, so we know the electron wavelength, we know the spherical aberration. And this essentially describes how each spatial frequency is going to be transmitted by the objective lens of the electron microscope. So the way I found that it works best for me to try and understand this effect is using these argon diagrams again. So what you can see here is we have our unscattered wave, and then we have our scattered wave, but this is essentially at low scattering angles. So what happens is we have this induced 90-degree phase shift due to the effect of scattering, but because the path length change is very small because of the low scattering angle, this remains, it basically doesn't interfere with our unscattered electron. So the amplitude of the sum is the same as essentially the same as the amplitude of the unscattered. So therefore we don't see any contrast. As you go further out, as your scattering angle increases, you get to a situation where you induce an additional 90-degree phase shift. So that's 90-degree from the scattering plus another 90-degree, which gives you 180-degree phase shift to your scattered electron. And then when you sum the unscattered with the scattered wave, you get a reduction in the amplitude of your sum, which your detector will see as negative contrast. Then if we carry on going, so we go out to further scattering angles, we can get to the situation where we can have an additional 270 degrees phase shift from the path length difference between the scattered and unscattered electron waves. And this will, again, so this is now additive. So the sum of the scattered versus an unscattered is amplitude is higher, so we'll see this as positive contrast. And then this starts to look like the standard kind of contrast transfer functions that we see from the microscope, where we start with negative as the scattering angle increases. As you go up to higher spatial frequencies, you get maximum negative contrast. So this spatial frequency is represented fully, and then you go back to where there is no transfer at this spatial frequency, and then again it flips, so you now have maximum positive contrast and maximum transfer of this spatial frequency, and again going down to 0. So wider focus. So as you can see from that first graph, or from the previous slide, at low scattering angles, which are equivalent to the kind of coarse details in our images, we don't get any real path length change. So we don't get essentially those spatial frequencies are either not transferred or not transferred very well. So we just are not able to see the object. So essentially what we're doing is defocus allows us to change the spatial frequencies that are represented in our image so that it makes it easier for us to see our object of interest. So this is just a very old image, just showing this tricolon protease from Tom Volz's lab. And this is just with a difference of 2 microns and 7 microns under focus. So again, if we go back to our argon diagrams, what that means is that this additional kind of phase shift that we see through path length difference between our unscattered and scattered electron wave is shifted towards lower spatial frequencies, which means that those spatial frequencies are transferred better by the objective lens of the microscope, which means in our image it's easier for us to see them. So this just shows you some ideal CTF curves from with varying amounts of defocus. So you can see, again, we start off with very little transfer of spatial frequencies at the lower end. Then we get a maxima, and then goes through 0 again, where we get no transfer, then to a positive maxima, then back through 0. And you can see that this function oscillates. And so this is comparing 0.5 to, so 0.5, 1, 2, and 4 microns into focus. So what you can see is you get this oscillation effect, and as you increase the focus, you shift that initial transfer of spatial frequencies towards the lower end, which makes it easier for you to see your object. The problem with that is that you increase the number of spatial frequencies that are not transferred, and as you go up to higher spatial frequencies, you can see you get these very rapid contrast reversals. And this is again shown with some images that I took quite a while ago with Cryo-Electron, which used to be one of my favorite proteins. So if we again have a look at these effects, so you've got the real space images at the top, and then you've got the Fourier transforms below. So this is just in frequency space. So you go from kind of coarse details at the origin to fine details out near the edge of the box. So, and that corresponds to low to high resolution again. And what that means is you can see here, this is quite close to focus, and it's quite difficult for us to see our objects. They are there. But as we increase the defocus, it becomes easier and easier for us to see our objects, because the low spatial frequency, the power of those is transferred into the image, and it just makes it easier for us to see our objects. But again, you know, as I said earlier, the problem with this is it increases the number of contrast reversals. The other thing that we need to mention is, so the ideal curves don't show any kind of amplitude fall off, but in reality, due to how should we say, the optics, what we actually see is not only do we see these kind of oscillations, but we also see this kind of, an envelope effect where the higher spatial frequencies corresponding to our fine details are dampened. And again, this is just shown in the Fourier transform from these images of carbon film at 0.5 and 1 micron under focus. So this envelope function is caused by a number of different things. So there's a loss of spatial coherence, which can be associated with the source size. So FEGs have a very small source size. So essentially most of the electrons are emitted from the same point. Whereas if you, for example, went to a tungsten filament, you get electrons emitted from different points. They can have different tilts. So they are basically spatially incoherent. And so they'll be focused to different planes in the microscope. And it will just mean that you won't be able to get the nice tone ring patterns that we saw on the previous image. There's also loss of temporal coherence, which is the energy spread. So not all electrons that come out of your source have the same energy. And that has, again, a similar effect in that your electrons are not focused to the same point. So it causes a blurring and a loss of signal, particularly at higher spatial frequencies. There's also image drift, which, you know, used to be a major problem for us, but now with motion correction, it's less so. I mean, it's still not solved. There are beam-induced motions and things like that, which still cause issues. There's obviously ice thickness, so that has a big effect on this. Thicker ice, you get more loss of electrons via inelastically scattered. So you get a loss of signal. There's also, you know, specimen charging, so grid type and support, and there are various aberrations associated with the microscope that also, all of this together gives you this kind of envelope function, which means we don't transfer high spatial frequencies as well as low spatial frequencies. So this is just shown in a graph here where you have applied a beam tilt of 0.9 millirad. So that's a pretty small beam tilt. So you've still got reasonable transfer of spatial or high spatial frequencies at 4 microns. This would be much worse if you increase the beam tilt. So again, we can have a look at the drifts. So if we take an image of a drifting piece of carbon film in this, so if we look at the defocus of that, or if we plot that defocus, we get these nice tone ring patterns if there's no drift. But then as soon as we start adding drift, particularly as most of the time when you're doing CTF determination, you radially average these power spectra. So you can see that you get a loss of signal at higher spatial frequencies. But again, a lot of these effects are, how should we say, reduced with the motion correction that we can now do with the direct electron detectors, as long as you remember to turn off the turbo pumps on your microscopes. So a lot of what I've talked about so far has kind of revolved around the contrast transfer function, which is primarily in reciprocal space or Fourier space. But this effect can be seen in your image, and it's called the point spread function. So if you look at an in-focus image here of one of Lena's favorite objects, this dotty elephant, you can see that you've got quite a nice transfer of the dot. It looks pretty sharp. It's a bit blurred, and that you can see is because there's an envelope function. As you increase the defocus, you delocalize your signal further and further out into the image, and you see these concentric rings. And again, so the CTF is just the Fourier transform of this point spread function. But it does mean that as you increase the focus, you really have to take this into account and thinking about box sizes that you're going to cut your particles out into. And then if we look at the effects of the contrast transfer function on some 2D projections of GROW-EL. So if we go from kind of very close to focus 5 nanometers out to 3.5 microns, we can see this effect of a kind of a blurring of our object. So we start to lose some of the kind of fine details, or they're more difficult to see. And we can see this kind of effect of spreading of the information further and further out into the box. And again, if we look at that in 3D as well, we can see at 5 nanometers, we've got essentially a volume that looks pretty nice to about 15-ish angstroms. So our features look good. And as you increase the amount of defocus, you can see that the how should we say, the spatial frequencies that are represented in the image change, and you get this kind of blurring and a loss of information if it's not corrected for. So one problem that we do have is that to be able to determine the contrast transfer function, we need to be able to see tone rings in the Fourier transforms of our image. So, and that can be a problem, sometimes you don't see this if your ice is too thick, if you don't have carbon or scattering material in your image. So, as I say, if you have very sparse particles and you don't include any carbon in your images, then you're probably not going to see too many tone rings. And there's also, if you're too close to focus as well, or if you're using a non-FEG source. So measuring defocus. So probably the easiest way is to take your Fourier transform or your power spectra, and and rotationally average that power spectra, which should increase the signal of the contrast transfer regions and the zeros. And then essentially what you need to do is to measure the positions of the zeros, or the relative spatial frequency at which those zeros appear, and then you can plug that into your contrast transfer function equation, and it will give you the defocus. So there are multiple softwares that you can use to do this. So I did this with B-Show. This is primarily to show you, you know, one of the other things that you have to remember is that sometimes it can be a bit tricky to see your tone rings so over the background in the image, so through kind of incoherent scattering, noise, various other things. So lots of software allows you to basically define the envelope and subtract the background, which can make it easier to see, particularly your contrast reversals at higher spatial frequencies. So if I just zoom in here, so you can still see out at fairly high spatial frequencies, we can see the ripples for these two images. And again, you know, so this just reporting the position of the first zero, and it tells us essentially the defocus. So there are lots of procedures for measuring defocus and for doing CTF correction. A lot of these you'll be doing in the practicals. So you know, EMAN2 has something. BSoft is what I showed you on the previous slide. CTF Fine 4, which is kind of one of the most popular ways to do the initial CTF estimation. So that kind of takes your images, kind of chops them up into boxes, tries to estimate the defocus, which you tell it over a certain range. It'll estimate something else called the astigmatism, which we'll go into in a second. And it does, you know, it produces some nice graphical output for you to look at. GCTF is also another very popular program for CTF determination, which does very similar things to CTF Fine 4. What you'll find is pretty much all single particle analysis softwares will correct for the effects of the contrast transfer function. And then if we look more specifically at some of the softwares for doing tomography-based CTF determination and correction, so iMod has a method for this, which I'll show, and Nova CTF, which was a way of doing 3D CTF correction from John Briggs's lab. So these are just some of the outputs that we routinely get. So on the top panel here, we've got CTF Fine 4, so you can see your experimental power spectra as 3/4 of the image, and then the estimated power spectra it gets by estimating where the position of the zeros, and it will spit out a defocus value. It will generally give you two defocus values, as an angle of astigmatism and a score, and it also gives you the confidence of where it thinks it can measure the contrast reversals up to. So in this case, 2.7 angstroms. Again, GCTF does essentially the same thing. So okay. So astigmatism. So this is again one of the things that you have to be aware of. So if you don't, or if you have transfer of spatial frequencies is not symmetric with your objective lens, you'll see these kind of elliptical tone ring patterns when you calculate your power spectral Fourier transform from your image. So what that means is, if you look here, you have two directions of astigmatism. You have the close to focus and further from focus direction. And if we plot those if we plug that defocus into our CTF equation, we can see that that would significantly change the position of the contrast reversals and the zeros at higher spatial frequencies. So you don't see this at low spatial frequencies, but particularly if you're trying to get to high resolution, this is something that you need to be aware of and need to be able to correct for. And so, you know, to measure that, you essentially have to assign the kind of the major and minor, or the minimum defocus axis and the maximum defocus axis. And most CTF estimation programs do this, and then you can kind of fit this elliptical pattern, and then you can correct for that when you do your CTF correction. One of the other things that we also need to consider when we're actually doing this for real on a data set is that at a particular defocus value, the contrast transfer function has zeros in specific positions. So that means we don't have transfer of information at those positions, and close to those positions, we have pretty unreliable transfer. So if we were to just generate a structure of our object using just one defocus, we would have some missing information. So what you need to think about is that you need to collect a range of defocuses to try and plug in the gaps. So, you know, at the first defocus, we can see we have zeros here. So if we increase the defocus, so use slightly more defocus, we can see we shift that first zero. So at the first zero in the red curve, we can see that we have maximum transfer in the purple curve. And so this is one of the things that you need to think about when you're doing your experiments, is the range of defocuses. So kind of standard ranges are kind of 1 to 2.5 microns under focus for normal sized objects. If you're looking at something particularly small, then you may want to use slightly higher defocus range, maybe 2 to 4 microns. But again, you just want to make sure that when you look at your contrast transfer functions for all of those defocuses, that you fill in the regions which are not transferred using different defocuses, and then you can, if you look at the sum, should be much closer to something like this, where you get transfer across all spatial frequency ranges. So methods for CTF correction. So the first thing that we need to compensate for is essentially this. We have contrast reversals, so they have the opposite contrast to each other, and that's incorrect. So the simplest way to correct for that effect, and what we used to do routinely, is to do something called phase flipping. So this, you just essentially apply a box function with +1, -1, and you multiply your Fourier transform of your image with that, and that will flip all of your spatial frequency ranges, so at least they have the same contrast. So that means all of the features within your particle should now have either negative or positive contrast, depending on how you do that. So yeah, but that doesn't compensate for the envelope effect that we see with the loss of amplitude at the higher spatial frequencies. So the way to do, or one way of correcting for that, is to essentially, instead of multiplying by this box function, you multiply each image by the Fourier transform of itself, and then you add, how should we say, this needs to be done with a collection of particles, or even better if you can do this on the 3D, where you have all of your defocuses in there. So you initially multiply them to correct for the contrast reversals, and then the final step of the CTF correction is to then divide by, so if you have all of your particles, so all of your CTFs multiplied by the CTFs, then you can divide the sum of those by the sum of all of the CTFs squared plus a parameter that we have to use this so-called Wiener factor to avoid a division by 0. And so this is called the full CTF correction, and this will restore or at least go as best as we can do for the moment to restore the amplitude fall off that we get due to the envelope function of the microscope. But this Wiener parameter is something that we have to play around with. So you have to be a bit careful when you're doing this, because essentially, if you use too large a Wiener factor, you will, it's like applying a low pass filter to your data. So you will smooth out any high resolution information. So again, this is just shown graphically. So, the green curve here, so the blue curve is your image with this oscillating contrast transfer function. The red curve is the multiplication of that with itself. So that causes the flipping. It also increases, how should we say, large numbers multiplied by large numbers give you a larger number, and small numbers multiplied by small numbers give you a small number. So it increases the power of well transfer frequencies. And then at the end, you would do this division by the Wiener filter, sum of the CTF. The other thing that I wanted to mention, which is not something, how should we say, when I was doing my PhD or for a chunk of my postdoc, I really worried about was aliasing of the CTF. So this is particularly something if you are working on, so a fair number of things that I do are kind of standard data sets. So I want to make sure my microscope's working. So I'm going to put apoferritin in there. I'm going to collect some data, and I'm going to see, how far in resolution terms I can get with it. So as you go to higher and higher resolutions, you really have to consider aliasing of your contrast transfer function. And this is essentially down to the box size that you cut your particles or particles are extracted in, and the pixel size of that box. So as you increase the defocus, so if we, on these 3 diagrams here, so if we have this ring, you see about 2.5 angstroms. So this is our contrast transfer function with this box size and this pixel size at 0.5, and you can see these nice tone ring patterns going out. As you increase the defocus, you can start to see these kind of weird reflections coming back in. So this is this aliasing effect, where you still have information at the what's the best way to at the limit of sampling, which is reflected back into your image. And again, as you increase the defocus, if you keep the box size the same, which is what you would normally do for most data sets, you can see that these effects, they start out at higher spatial frequencies, but as you increase the defocus, they start to appear at lower spatial frequencies, and essentially they just add noise to the, so you're not correctly correcting for the contrast transfer function. And so this is from Dustin. So the slide before was from Takanori's got a really nice little web page. It's listed there for calculating, what kind of, based on box size and pixel size, and based on the resolution that you're trying to get to, it will tell you where this effect, where aliasing starts to have a major effect. So I can highly recommend using that. Also, Dustin has a nice kind of blog on this, where he has essentially calculated the box size or shows this graphically where aliasing will start to have an effect. And also on this same page, there was a kind of a Twitter thing from Rado. So there's, again, quite a nice little, fairly straightforward formula that you can use to, based on the resolution that you expect to achieve, what kind of maximum defocus that you can use is. And so if you look at some of the highest resolution apoferritin structures, for example, they use very close to focus images, so from 300 to 1,000 nanometers, so 0.3 to 1 micron under focus, because if they don't do that, they would have to increase the box size, which would make it, how should we say, the processing, it just makes it more complicated in terms of it takes more space, and you eventually reach a box size that you can't actually get to run on your GPUs because you don't have enough memory. So the other thing I wanted to mention with kind of CTF correction is rely on, and there are a number of other softwares, so FreeAlign System, that also do this, allow, how should we say, more complicated CTF refinements further down the processing. So the way that Relion does this is it allows you to, how should we say, maximize the cross correlation between your reference structure with CTF parameters and your experimental image. And this allows you to, this is just much more sensitive to the kind of the correct contrast reversals and positions of zero. So this allows you to extend the resolution of your structures. So yeah, and it can be used to estimate the per particle defocus. So anyway, in my experience, this has probably the biggest effect when you do processing within Relion. So then if we move on to defocus when we're looking at tilt series tomographic data, so that kind of gets more complicated because what you're essentially doing when you tilt your specimen is you're changing the height of your specimen relative to your objective lens, which essentially means that you change the focal point of that particular region. So this is from the kind of IMOD course. So if you look at this image, it's tilted at 65 degrees. And if you look at the tone ring patterns from different regions, so on the tilt axis, and then you know, the kind of most, or the furthest away from the objective, or the closest to the objective, you can see that you get this defocus, this variation in underfocus. So that's one thing that you have to be aware of when you're looking at tilt specimens, is that you have a defocus, essentially gradient across your image, depending on its relative height to the objective lens. So again, this is just shown here. So if we look at this kind of tilted specimen, so you know, this is for, okay, it's a CCD image, but most of our images are still around 4K. So it means you roughly would have a 1 micron difference in defocus from one side of the specimen to the other. So the way that IMOD does this is it allows you to estimate the defocus of this tilted in regions. It will give you an average defocus and it will give you a tilt angle. So it essentially knows what the defocus change is as you go to different parts of the image, and then you can correct your for the contrast transfer functions in strips. You know, so if you know where the tilt axis is, you know that the distance from the tilt axis is equivalent to a change in height, and so equivalent to a defocus change. So this is one way of correcting for the effects of the CTF in tilted specimens. There's also a more, how should we say, complicated way to do this. So what you can do is what Nova CTF does, and essentially it tries to tries to estimate the height of your objects within the volume, and depending on the height of your objects in the volume, it will take a defocus value. So it will take your tilt images and apply multiple defocus values, but it will take the appropriate defocus value for the relative height of the specimen in your volume. So it can correct for also height differences within the volume. Yeah, and this works very nicely. So the final thing that I'm going to talk about is kind of phase plates. So this is, how should we say, they were quite popular a few years ago. They're kind of a bit less popular now, but because there's a number of associated issues with the, how should we say, the current generation of phase plates. But essentially what they do is you have something that sits at the back focal plane of your objective lens. So there are two different types that have both been used. So there's the Zernike faceplate here, where you have so essentially your unscattered electrons at the back focal plane go through at the origin, very low, because essentially there's no scattering angle. And so they're in the Zernike faceplate, they're allowed to go through. Your scattered electrons at the back focal plane, depending on their angle, are then phase shifted by a carbon film that sits at this back focal plane. And so when that is recombined in the image, it induces an additional phase shift in your scattered electrons, similar to you applying defocus, in that you, for maximal interference, you want a further 90-degree phase shift. So that's Zernike. With the Volta faceplate, which is, how should we say, the most common type of faceplate, this has, again, a piece of carbon film, this time without the hole, so everything goes through the carbon film, including your unscattered electrons. But what you do prior to using the faceplate is that you generate this so-called Volta potential, where you generate a charged region, a very small charged region on this carbon film, which has the effect of accelerating your unscattered electrons relative to your scattered electrons. And depending on the amount of charge, this acceleration varies. So you can go from, so it just increases the relative phase difference between these two, and that's obviously dependent on the charge. So you can go from, you know, a high, or so you can increase the amount of low spatial frequencies that are transferred because you increase the relative, I suppose, path length. Well, it's not path length, but you change the phase relationship between the unscattered and scattered. So what this essentially looks like is, if you take so that, again, this is apoferritin on graphene, got the real image, power spectra. If you if you take this with standard phase contrast, you can see that, oh, it's 1 micron in the focus, so you can see the particles quite well. If you use the Volta faceplate, so this faceplate probably had was increasing the relative phase shift of the unscattered versus the scattered by an additional 90 degrees, so close to maximum interference. You can see that you can see your objects very, very clearly. So yeah, and it gives you a massive increase in the contrast of how well low frequency or coarse details are transferred by the microscope. So again, depending on the charge of the Volta potential, this will build up over time as it's used. So when you start up at low charges, you get small relative phase shifts. You still get an increase in contrast because your unscattered wave is accelerated to a lesser extent than at 90, but still accelerated versus your scattered. So you still get this interference, so it makes it easier to see your object. But as the phase shifts increases over time, as the charge builds up in your, you get higher phase shifts, so it becomes easier to see your object. But you also get a change in the tone ring pattern. So the positions of the zeros changes as the phase shift increases. So this essentially means that you can use or potentially use a single defocus value and rely on the changing of the volt potential to give you this kind of fill in the regions which are of spatial frequencies which are transferred in some images and or not transferred in some images but are transferred in others. Yeah. So essentially what the Volta faceplate is doing is it's kind of converting your contrast transfer function from a sine to a cosine, where you can see at 20% we've got transfer of low spatial frequencies, but as we increase this we get to a maximum transfer of low spatial frequencies, which makes it very easy for us to see our object. The problem with the faceplate and why it's become, I think, less popular is you get a loss of signal. So this was estimated to be kind of around 18% by Rado in this 2014 PNS paper. So you get an increased kind of envelope function of your microscope essentially, so you don't transfer high spatial frequencies as well. I mean, there's also some additional issues in the way that you collect the data with the Volta faceplate restricts how many images or how much image shift you can use. And so, how should we say, the newer methods for data collection you can't use, so you're going to reduce the number of images that you're able to collect in a set time period with the Volta faceplate. The reason that people would still use the faceplate, and I think, okay, I think you can still do structures of sub 100 kilodalton proteins without the faceplate. But what it does do is certainly has a big effect for small proteins, and this is where the kind of real advantage of the faceplate was this is why people started using it. So this is just the structure of streptavidin. So this is a 52 kilodalton protein solved to kind of 3.2 angstroms with the faceplate. So when I started EM, this was impossible. Even 450 kilodalton structures were pretty tricky depending on them, but these days they're easier. I'm just showing this as an example because this is one of the things we tested our faceplate with. Okay, so that's kind of all of the stuff that I wanted to talk about this morning. So I've got a load of references for all of the various things I've talked about today. And finally, for the last kind of couple of minutes, I just wanted to do a plug for EBIC, which is the facility I work at, based at Diamond. So EBIC is kind of the UK National Centre for Cryo-EM. So we offer kind of free at the point of access facilities through a kind of peer-reviewed application process. We try and operate in a kind of beamline like fashion, so 24/7, and we run a pretty large external user program. So yeah, if you don't have access to higher end microscopes, please go and have a look. We also have in-house research programs. So we have a director in Peijun who has quite a large research program, and then there are kind of PBSs under Pejun, including Alistair, who's just about to leave us to go and work on a different project. So we all have in-house activities and projects that we're doing. We're kind of trying to act as a hub to, integrate structural biology with other developments. So, we have CCP-EM on site. We have iNext. We're involved with iNext, so for European access. We also run remote, or we're also involved in training courses, and Kyle Morris has just come on board as our training officer. So if you're looking for kind of training opportunities for Cryo-EM, I would definitely have a look at the EBIC site in the near future, because there's going to be some more courses. We recently ran a remote data collection course in April for Instruct, and the next course is, I think, going to be announced fairly shortly. So we have, this is just some images of our kind of Cryos facility. So our main Cryos hall. So we have 4 Cryoses in this room. We have Cryos 1, the original, still on the hall floor of the main synchrotron building. We have a centralized control room where we can control all of the Cryoses. So currently we have 5, and we have controls for most of the smaller microscopes there as well. So this just shows you again the list of equipment that we've got. So we've got we also have the Sios and Aqualos, so Cryofib SEM for preparation of cellular material. So again, if you're interested in that, please contact me or James. So just go to our website and have a look. We have recently moved our Bioquantum K3 onto our Talos. So this is going to be kind of our in-house, well, it is our in-house machine, but we're also going to put a lot of training that we're going to offer onto this machine. And we're also just about to put out a call for microED. We also have a chameleon for doing freezing, which is a collaboration with the RFI and SPT, who make the chameleon. And again, if you're interested in trying the chameleon, please have a look at our website. And we also have a Leica CryoClem, which will hopefully fit into the workflows that we have for the Sios and Aqualos. And we're just about to put out a commissioning call for this. So again, have a look at the webpage. And just to say that, so the most recent update we've had, so we were already using APHIS, which was the aberration-free image shift collection within EPU to speed up data collection. But we've now just finished the upgrade of all 4 of the academic Cryoses anyway, to allow for fringe-free illumination. So that's this reduction of the Fresnel fringes that you get from your C2 aperture, which means you can use much smaller illuminated areas, which means you can take more images per hole, and which increases the speed. So I think with kind of optimal pixel size, mag and dose, we're up to about 1,000 movies per hour for optimal, the fastest we can go. And there's, as we say, there are a lot of people involved in this. We have Dave Helen and mine and Kai as on our executive committee, who kind of help us with the directions that we're going. We have an industry specific team kind of headed up by Jason. And there's a lot of people at Diamond who make this happen. And I think that is me done. So I think we can end the lecture. And so if you've got any questions, now's the time. Thanks for listening.